Okay, so this is the last lecture, lecture 27. Actually, maybe it's lecture 27,000, I don't know. Seems like we've been doing this forever. So primarily what I want to do today is open it up for questions about the exam and then discuss that final example about confidence intervals. So homework 5, first of all, central limit theorem. I did that in class last time. It does not have to be handed in for credit, should not be handed in for credit. But I'm assuming from for the purposes of the exam that you did it, just as if it were handed in for credit. So you don't have to make the calculations. I did them in class. If you run the simulation, it'll just convince you that what I said is true, so it's not necessary to do that, although I would recommend it. But so you're responsible for it for the exam, but there's no points associated with it. Don't hand it in. Don't worry about it. Or don't worry about it as far as that homework grade goes. Are there any questions about it? All right, I'm going to illustrate its use shortly when I talk about confidence intervals. As far as the exam goes, remember it'll be in GCS 118, Tuesday, 4 to 6:30. It'll be open book, open notes. You should bring your homeworks with you. I assume that you have all that stuff in front of you and that the exam will refer to the homework problems. So I will say things like, suppose that in homework 3, such and such were true. Then do this. So if you understand the homeworks, to a certain extent, there are things that are straightforward that you should be able to do. As far as the open book aspect goes, make sure that you bring in a calculator. I don't know whether you'll need it or not, but a calculator and whatever tables you might need. So you cannot, they don't have to be your own tables, of course. You can Xerox tables from any place. You can borrow a calculator, but you cannot pass tables or calculators back and forth once the exam starts. So don't come in with your buddy and go back and forth with the calculator. Otherwise, straightforward, no cell phones. Although I guess a cell phone isn't any good unless you have someone to call who can help you. Probably you're worse off calling somebody on your cell phone and asking for his advice than doing it yourself. Otherwise, are there any questions about it? One other thing I should say is that just like the midterm, the design will be such that if you did the homeworks, then a large part of the exam should be straightforward. But there will be things on the exam that are not directly taken from the homeworks, although they're not things that are different. That is, it's not let me say it's not straightforward. Let me give an analogy. Suppose this were an English course, and people always want to know what to study. So for an English course, I could say, you have to know the definition and how to spell every word in the English language. That's pretty hard, but nevertheless, if you cared about it, you could do something. You could go get the dictionary that defines the English language and study. And then you'd know exactly what kind of questions were going to be asked, and your grade would depend to a large extent on how much effort you put in to memorize the dictionary. But that's pretty much useless information, actually. Another question you could ask is something like, using the fact that you know the words of the English language, pick any topic that has is controversial with two sides on which you have an opinion, and write an essay that summarizes the arguments for and against. In that case, there's no right answer. It's very subjective, but it's much more meaningful and it's much more difficult. So you can't study for something like that. That's something that you sort of absorb it in the time that you're studying English, but there's no way you can go home and say, okay, unless, even if you knew the question in advance, it's really hard to study for it. You have to know what you're doing. So this test will be similar in the sense that some of it is like, how do you spell these words? That's the stuff that's taken directly from the homeworks. Others are, one or two questions will be things that you can't study for in advance. It's just if you understand what's been going on in the class, then maybe you can do these. And if you can't, you can't. But when you get out into the real world, if you're ever going to use probability, the important thing will be, can you solve problems that are not exactly the same problems you've seen before, or not textbook problems where you can look up the answer in the back of the book, because nobody's going to ask you to answer a question that can be obtained by looking it up in a textbook. If you're going to use this stuff, you're going to have to use it in a creative way, and the purpose of this course is to give you the tools so that you could use it in a creative way. And the purpose of the test is to see whether or not, in some cases, whether you know the tools, and also whether or not you can use it in a creative way. So it's like the midterm in that sense. It's just that I'm trying to say that some people always like to say, what should I study? And the only thing you can study for that's focused, I say, is study the homeworks. And if you do that, hopefully you'll see the whole thing. So any questions about that? Yes.
Are you going to be required to write code?
No. I could ask you to write code for using the inverse transform method, but I don't care about the syntax. All I care about is if you understand how the inverse transform method works. So I guess the answer to that is no. There's no code as such.
You might be asked to come up with a formula or inverse.
Yeah, I might give you a density function, let's say, and ask you how you would generate values from a population that has that density function in the simulation. And then you would use some basic-like instruction. In other words, you would solve use the inverse transform method to solve backwards, and then try and express that in basic type code. But if it's mathematically correct, logically correct, that's what I care about. I don't care about the syntax. Yes?
The material we had on the midterm, is that included in the final?
The question is, will the stuff on the midterm? There won't be anything on the final that's directly related to the midterm like combinatorics, no poker problems or anything of that nature. On the other hand, what you've been doing in the second half of the course is you've been calculating probabilities and parameters like mean and variance for certain kinds of populations. And those probabilities follow certain rules, which are the rules that we derived in the beginning of the course, like the probability of a union is the sum of the probabilities, that kind of thing. So in that sense, it's continuous. But in the sense that you have to go back and look at some of these really tricky things about how you count poker hands, no.
In other words, nothing will look like the midterm. It will look like the homework.
It looked like the homeworks. But that doesn't mean that every question can be mapped into a specific homework question. Okay? Because the objective of the exam is twofold. One is I want to see whether people get the main technical points, and then to differentiate the ordinary C's and B's from the A's, which are the people who presumably understand the subject fairly well. Then there'll be one or two harder problems. And you can't really study for the harder ones.
So there will be nothing that is mapped directly to the midterm?
Nothing directly to the midterm, no. But what I keep on saying is that the material that preceded the midterm, you don't just forget that, because in fact that was used in the second half of the course. The way to study is to go over the homeworks and make sure you not only know how to do what was done, but try and look a little bit deeper and understand what the homeworks mean, and ask yourself, if you were an instructor teaching a course like this, how could you come up with an exam that would test whether or not people know the basic stuff, and give something that would discriminate between the people who should get an A and the people who shouldn't get an A.
So if we are studying and we get to exam, right, there's something that we don't understand, or we don't have no friends to call on, how can we get to do it?
At this stage, there's not too much you can do. I mean, if you can find me, okay. I'll do my best to hide. but it's late to be asking those questions. But if you can find me, okay.
How about anything after homework?
The stuff on confidence intervals will not be on the exam, and there will be no calculation that involves a convolution. So the stuff I'm going to talk about today, when I start talking about confidence intervals, you can all walk out if you want. I'll turn my back. Okay, so anything else? Anybody that I owe homework to? I have some, let's see. Thank you. Lanoff, Barr, Lambro, Paraskeva, Khalil, all right, so the stuff I'm going to talk about now should be interesting because I think it relates to things that you're somewhat familiar with. And the thing about education is that people, it's hard to force people. People generally will not voluntarily study things or think about things that it would turn out are actually interesting. But if it involves intellectual effort, they don't do it. That's why you have to make people take exams and force them to get grades on homeworks and things like that. On the other hand, if you actually sit back and try and concentrate on it and know that you don't have to worry about taking an exam so that the pressure is off, that's the best. So the way to go to school really is to just go to some university, take courses that interest you, hang out, and but don't waste your time totally. If you could afford that, that would be the greatest. Of course, that doesn't work. But this is your chance to do that today because what I'm going to talk about is not going to be on the exam, so you can either listen or not. So I want to talk about confidence intervals, which we already discussed somewhat. And this is section 7.3 in Ross. I think the main thing we need for this course is good markers. That's sort of me. Let me see if I can do better than that. We don't even have anything here. So this is 7.3. That's not bad. 7.3, which is on page 223. And the idea is that we have this population. So we have this urn with tickets in it. And the values of the tickets are called X. That's the random variable. And we assume that we're going to sample from the urn n times. So this is the first value, that's the second value, and so forth. And we assume that there's an expected value that we know, or that we maybe want to know, which we'll call mu, and a variance that we'll call sigma squared. And we'll define x bar as the average, which means you add these x's up and you divide by the number in the sample. And what we know then, for all practical purposes, is that if we take this new statistic, which is the average minus the expected value, divided by the standard deviation, which is the square root of the variance, divided by the square root of the sample size, if that thing is essentially normally distributed with parameters 0 and 1, the standard normal distribution. And this is what was tested in the homework problem, homework 5. Now, based on this statement, we can do some manipulation. And the manipulation is this. So I asked you to do this yourself. It's just algebra. I don't want to spend time doing it. I just want to get to the answer. So here is the standard normal density function. So this is 0. And we imagine that there's a value here which we call z sub alpha over 2. And then there's the value over here, which is the negative of that, minus z sub alpha over 2. And by definition, z sub alpha over 2 cuts off an area here, or a probability, equal to alpha over 2. And similarly, by symmetry, that cuts off an area equal to alpha over 2. And since the total area must be 1, that means that the area that remains must be 1 minus that plus that, which is 1 minus alpha. Now, we can then write this statement. The statement is, I'll write it here. the probability that mu lies between x bar minus z sub alpha over 2 times sigma over the square root of n and x bar plus z sub alpha over 2 times sigma over the square root of n equals something. Okay, now, this is an interval. This is derived from this statement right here, if we were to write this out algebraically and then simply manipulate things. Multiply through by -1, rearrange. It's just algebra. When you get done with writing it in this way, what this says is that there's a certain probability, which I'm going to write here, that in a random interval, this is a random interval because x bar is a random value. It's the average, which is random. And so I take that average and I subtract something, which is a constant, and I take the same average and I add that constant. So I have an interval. And the probability that that interval covers or contains mu, which is the expected value of the population from which we're sampling, that probability is given by the following. From the central limit theorem, that's equal to 2 times capital phi. Let's see if I can find a better one of these. Okay, let's try blue. Okay, we have 2 times capital phi, purple, anyhow you can see it, of z sub alpha over 2 minus 1. Okay, so we know that from that statement about the probability that something that has a standard normal distribution lies between two symmetric limits. So we've seen that before. And this is also equal to 1 minus alpha by the definition of alpha over 2. Because what we've done is we've calculated the probability that basically that we cut off an area whose value is 1 minus alpha. Okay, so I did this in class last time, and in fact this statement is on page 226 of the textbook. So we could say then this: a 100 times 1 minus alpha percent two-sided confidence interval for mu is, and then we have this interval whose limits, whose boundaries are x bar minus z sub alpha over 2 times sigma over the square root of n, and x bar plus z sub alpha over 2 times sigma divided by the square root of n. So in other words, if I give you a value of alpha, typically it's 5%. So that means that 1 minus alpha is 95%. So in that case, we would say a 95% two-sided, because it's got two limits here, could be one-sided, meaning one side is infinity. So a 95% two-sided confidence interval for mu is, that means that the probability, if I took alpha to be 5%, the probability that x bar minus this and x bar plus this will contain the actual expected value between them is 95%. And what we want to do is we want to figure out what these guys here are so that we have a meaningful statement. So now I'm going to give an example of that and then show how that's used in polling or surveys. Okay, so let's say, suppose alpha is equal to 5%. Okay, so this is arbitrary. I can make alpha anything I want, although alpha as 5% is often used as a convention. So first of all, why is that? I could say then capital phi of z sub alpha over 2. That's equal to 1 minus, okay, now remember that that's going to be equal to the area to the left of this point z sub alpha over 2. And if alpha is 5%, and alpha over 2 will be 2.5%, so the area to the left of that will be 97.5%. So this is equal to 1 minus 0.05 over 2, which is 0.9750. Okay, so now we go to the table. Table A1 in Ross, and what we find is that z sub alpha over 2 in this case is equal to 1.96. Okay, so if you go to the table, here's my table. The table looks like this. It has the values of x, and then it goes 0.0, 0.1, and so forth. And if you go down to 1.9, and then over to, here's 0.00, 0.01, and so forth, and here's 0.06. So the entry right here would be the value that would be capital Phi of 1.96. Now, if you look that up in the table, you will see that this value right here is exactly 0.9750. So one of the reasons that people like to use 95% confidence interval, alpha equals 5%, is because when you figure out what the value of z is, it's going to fit in your equation, you find that you don't have to interpolate, but it's right there exactly in the table. So that makes everything very nice. So people tend to remember this. Everybody thinks of z, the typical value of z for confidence intervals, as being 1.96. Okay, so what that means is that, therefore, I could say that x bar minus 1.96 sigma divided by the square root of n, and x bar plus 1.96 sigma divided by the square root of n is a 95% confidence interval for mu. Okay, but the question is, how can I use this? Of course, the n can be anything I want. That's my sample size. But what's the sigma? So you could say, well, this isn't really very useful because, after all, if I don't know what mu is, if that's what I'm trying to find out, I'm trying to get a statement about give me some bounds such that I have a 95% probability that those bounds will contain mu between them. Mu is the thing I don't know its value. If that's the fact, that I don't know mu, then how can I expect to know sigma? And there are various answers for that. One answer is, well, we're starting at the beginning here, so let's take the easiest thing we can do. If we knew sigma, then we could use this. Another argument is that maybe I could estimate the sigma, and if I estimate the sigma to be as large as it could possibly be, that means that then my conclusion will be on the conservative side, because I know that the bigger sigma is, the more uncertainty I have. Remember that the sigma, which is the square root of the variance is a measure of how much variability there is. And it's the variability that's the heart of all the problems. If everything were constant, then we wouldn't need any statistics. We could figure out what was going on in the population by simply sampling one value, and all the other values would be exactly the same. So we want to apply that in the case in which the sigma is going to be estimated to be the largest it can possibly be, and show that that makes sense. So I'm going to do that by referring to election polling. This is an example of the application of this that everybody sees all the time. And so what's going to happen is I got this population now, and the x values, what's in the population, actually represents the votes of the voters, or what the voters, how the people say they're going to vote. So each person I could sample could say something like, for example, Bush. In fact, the figures I have here are from the, I think they were from the governor's election. And Bush was running against somebody who I don't even remember his name. That just goes to show you how that went. But in any event, there's Bush and the other guy. And what happens is you ask a voter who he's going to vote for, and he says Bush or the other guy, and then based on a sample of a few voters, you try and say that represents a fair sample for the whole population, and so you project the outcome of the election based on the sample. So you want to see how accurate that is. That's what happens all the time in opinion polls when the newspaper says that Bush is leading 60 to 40 or something like that. Okay, so the way I want to model it is this. I'm going to imagine that we have these tickets in there. Each ticket represents a random selection of a person who's going to tell you how he's going to vote. But I'm going to express it this way. I'm going to let xi, that's the value of the ith ticket that I pull out, the ith sample, I'm going to let it equal 1 if the person says he's going to vote for Bush, and I'm going to let it equal 0 if he's for the opponent. Okay, now, then the probability that xi is equal to 1, let's call that p. Probability that xi equals 1, let's call that little p. So the probability that if I sample and the person says he's going to vote for Bush and gets a 1, what I'm asking for is what is the probability that if I select a person at random, he will say that he's a Bush voter? And let's say that that's p. So this is now the probability that a randomly selected person is a Bush supporter. And of course what probability means is frequency, which means that if I can figure out what this probability is, if this probability is, say, 60%, what that means is that 60% of this population is going to be supporting Bush and 40% will be supporting the opponent. So the p, the probability that this random variable has the value 1, is equal to the fraction of voters. Remember, probability means frequency. So it's the fraction of voters for Bush. Okay, now I can calculate the mu, or the expected value of this population. So what is that? What's the expected value of the x's here? Well, this is actually the simplest discrete distribution. X takes on two values. It takes on the value 1 with probability p, and the value 0 with probability 1 minus p. So the expected value would be 0 times the probability that xi equals 0 plus 1 times the probability xi equals 1. And of course this is 0 and that's p. So what you see here is that the probability, which is the fraction of voters who favor Bush, that in fact is equal to the expected value of this population. And so that's going to allow you to use the central limit theorem, because the central limit theorem gives us a confidence interval. I didn't write it here, I erased over there, but the confidence interval is for mu, the expected value. Okay, what's the variance? Variance, that's the sigma squared. Now, the way I'll calculate that is I calculate the expected value of the square of x minus the square of the expected value. The expected value of the square is 0 squared times the probability that xi equals 0 plus 1 squared times the probability that xi equals 1. So this part here is the expected value of x squared. And I subtract from that the square of the expected value. But the expected value is simply p, so that's p squared. So that part is e squared of xi. Okay, so what is this? Well, that's 0, and that's p. So it's p minus p squared, or p times 1 minus p. So in this population, then, the thing that we want to get, which is p, is in fact mu, and the sigma squared, the variance, is equal to p times 1 minus p. Okay, now notice that x bar, which by definition is 1 over n, the so what is that? What I do here to calculate x bar, to be able to use the central limit theorem, is I add up all the x's and divide by n. Okay, now, every x is either 0 if I vote for the opponent, or 1 if I vote for Bush. So this sum is actually equal to the number of people in the sample who say they're going to vote for Bush. If I divide that number by the number in the sample, then that's the fraction of the sample that say they're going to vote for Bush. The fraction of the sample that's going to vote for Bush is analogous to the fraction of the population that's going to vote for Bush, and that's what we're trying to see. We want to see how close it is, how close the fraction of the sample who says they're going to vote for Bush is in fact equal, how close it is to the actual fraction in the whole population that's going to vote for Bush. That's the question. Okay, so this is equal to the fraction of sample who support Bush. Okay, so I'm using this cleverness to be able to put this into a framework so that I can go back here and use the central limit theorem. So when I use the central limit theorem says something about the mu lying between the average minus something and the average plus something. The average, in this case, is the fraction in the sample that say they're going to vote for Bush. The 1.96 makes it a 95% confidence interval. The n is the sample size, and the sigma is the standard deviation, which is the square root of the variance. We don't know what that is, but we know that it's equal to p times 1 minus p, so maybe we can estimate it. Okay, so now I want to look at that. So let's see where I'll do that. I'll do that here. So what I want to do is, let's see, let me write it this way first. Okay, so x bar minus 1.96 sigma divided by the square root of n, this is an interval, and x bar plus 1.96 sigma over the square root of n. That is a 95% confidence interval for mu, which is the same thing as p, which is the fraction of people in the population who are going to support Bush. Okay, so now I'll say let little x equal the margin of error. Okay, now the margin of error, that's this amount right here, because what I have is I have this value for mu, or p, I think is the value, and it's going to lie between, with probability 95%, it'll lie between that plus that and that minus that. So I could look at this as being what's called the margin of error. So what I'll say here then is that this x, this margin of error, is equal to 1.96 sigma divided by the square root of n. So that means I can solve this for n. So if I multiply through by the square root of n, divide by x, and then square it, I find that n is equal to 1.96 divided by x squared times sigma squared. So the sample size is related to the x, which is the margin of error, and the variance. The bigger the variance is, the larger the sample size I have to take for any given margin of error to have a 95%, that's what the 1.96 gives me, a 1.96 confidence interval. So what I want to do is I want to find the max, the largest possible sigma squared. Okay, because if I find and plug into the formula the largest possible value here, then I know that for any given margin of error, if I sample that number of people, then my confidence interval will be at least a 95% confidence interval. because I know that n can't be any bigger than what I would get if I take sigma squared to be as large as it could possibly be. Okay, so what can it possibly be? Well, that's going to be the maximum value of, according to this formula right here, p times 1 minus p. So this is easy. Remember, this p is a probability, so it lies between 0 and 1. So here is p times 1 minus p, and here's p, and here is 0, and here's 1. And if you draw this graph, you'll see simply that it looks like that. You can see this, or you can use calculus. So obviously, when p is equal to 0, this value is 0. When p is equal to 1, the value is 0. And as p moves between 0 and 1, this product gets bigger, reaches a maximum, and gets smaller. And the maximum it reaches is right here at 1/4. So the maximum value is 1/4. It reaches it right in the middle when p is equal to 1/2. So in other words, the maximum value of the variance is 1/4. So therefore, I could say that if I pick n approximately equal to 1.96 over the error, margin of error, squared times 1/4, I will have a 95% confidence interval. So all I got to do is pick the margin of error, plug that in here, and then we have our confidence interval. Okay, so let me do that over here. Okay, so what I'm going to do is, I'm going to, for reasons that will become clear in a moment, I'm going to let x be 3.5%. Is there a question? Yeah. Came up with a quarter because I proved over here that the variance is equal to p times 1 minus p. Okay, so sigma squared is equal to p times 1 minus p. I want to get to pick the largest possible value because that's the most conservative estimate. Okay, so if p times 1 minus p is the variance, and p is a probability, it lies between 0 and 1, then if I want to take the maximum of this, I could say differentiate this with respect to p, set the derivative equal to 0 and solve, but I don't really need to do all that calculus. You can see that if you, this is just a parabola, and if I multiply this out, you can see that the graph looks like this. When p is 0, this factor, this product is 0, and when p is 1, this product is 0. And in between, it simply is symmetric about this line, p equals 1/2, and rises, reaches a maximum of 1/4, and goes back down to 0. So in other words, if you plugged p equals 1/2 in here, you'd have 1/2 times 1/2, which is 1/4. So this is the maximum value that the variance can be. So I just take that maximum value and I use it in this formula, and this tells me that if I want to have a 95% confidence interval for the fraction of voters who are going to support Bush, I have to question n people and then calculate the average and subtract from the average this amount and add from the average that amount, and with 95% probability, the true answer will lie between those two values. So all I need in order to figure out how many people to question to have a 95% confidence interval is to decide what margin of error I want. So I'm going to choose the margin of error to be 3.5%. That's arbitrary, but you'll see why I want to make it that in a moment. So I'll say let x equal 3.5%. 3.5% margin of error. So that means that when I get done here, if you look at this statement right here, if I'm going to plug in sigma to be equal to the square root of 1/4, which is 1/2, and plug in the value of n that I get from this equation, then I'm going to have some answer minus 3.5%, and the same answer plus 3.5%. So whatever the x bar turns out to be, there's a 95% chance that the true value of the fraction of people in the population who are going to support Bush will be within 3.5 percentage points of whatever x bar tells me. So that's my margin of error. Now, I could make the margin of error anything I wanted. Of course, if I make the margin of error bigger, what that means is that then my confidence interval gets bigger, which means that, well, let me write it out and we'll see what it means. Okay, so this is my 3.5% margin of error. Okay, so if that's true, that's my assumption, then from this equation right here, I plug in 3.5%, I do this arithmetic, and I get then N, the number of people I have to question, is approximately 1.96 divided by 0.035, that's my 3.5%, squared times 1/4. When you multiply that out, that turns out to be equal to 784 people. So what this says now is that if I assume that I have this population of people who are either going to be for Bush or the other guy, and I want to estimate the fraction of them that are for Bush, then what I could do is I can question 784 people and take the fraction of that sample that is for Bush, and then the probability is 95% that the true fraction of sample that's for Bush would be whatever that fraction turns out to be, plus or minus 3.5 percentage points. So, for example, if it turned out that when I took performed the experiment, that 60% of the people said they were for Bush, then I could say that with probability 95%, the outcome of the election will be that the actual result will be between 63.5% and 56.5%. That is, the observed fraction plus or minus 3.5% margin of error. Okay, now the reason I picked these numbers is the following. Here's a statement from the Miami Herald. And according to the Miami Herald, they questioned 800 people and had a 3.5% margin of error. And that's all they tell you. All right, now, part of my point is, let me read it here. It says here, there's a clip that's out of Miami Herald. It says, the governor's race. Source. This survey was conducted among a random selection of 800 registered and likely voters in Florida. The poll contains a margin of error of plus or minus 3.5 percentage points. Okay, so that's why I chose this as the example. For the full sample, and was conducted by Schroth and Associates, Washington, D.C., South Beach, and the polling company of Washington, D.C. So they have all this information here, and what they tell you is that they looked at 800 people and that they have a 3.5% margin of error. But what they didn't tell you was that it was a 95% confidence interval. Now, it might not have been. All I did was say, well, let's see. If I assumed that I had a 95% confidence interval, why did I assume that? I assumed that because if you assume 95%, then when you look things up in the table, you have a nice value like 1.96 without any interpolation. So everybody uses 95% because, well, it's close to 100%, and it's 1.96 is an easy number. Okay, so if I assume 95%, then I find out that if I question 784 people, I will have a 95% confidence interval with a 3.5% margin of error. Then I look in the newspaper and I see that they questioned 800 people. Well, that's pretty close to 784. And they have a 3.5% margin of error, but they don't say anything about whether it's a 95% confidence interval or something else. So basically what they're telling you here when they say they have a 3.5% margin of error is, to somebody who knows what they're doing, I can go backwards and say, that's probably has 95% accuracy. Somebody else, they have no idea what this means. Because certainly nobody thinks that for sure the answer that they get is guaranteed to lie within 3.5 percentage points. How do they know that? You can't tell exactly where it's going to lie unless you take sample the whole population. Which of course the whole point is that you're not going to sample the whole population. So they can't guarantee that it's going to lie within 3.5 percentage points. all they are saying is, well, it's pretty likely, although the ordinary reader of the newspaper doesn't look at it that way, he doesn't really think that deeply, he says, okay, it's whatever X bar turns out to be, or 60% or whatever they say, plus or minus 3.5 percentage points. But they didn't have to say it that way if they could have given you more information. So let me look a little bit deeper.
So from here you can work that back and get the confidence level, right?
What was that?
From there you can work it back and get the confidence intervals, right?
Well, I worked it back because in this case they told me the margin of error, they told me the number of people, and they told me the number of people. And when I plugged in, assuming it was 95% level of confidence, I got this number of people, which is pretty close to that. So I said, well, it's approximately 95% level of confidence. But ordinarily, sometimes they tell you that it's a 95% confidence like a level or something like that, which doesn't mean anything to most people. And they don't tell you the margin of error. I mean, there's different ways to do it. In fact, you could get several statements from the same data. And they almost never tell you all the data you need to uniquely figure out what's going on, because it's too complicated. Okay, so here is the general statement. X is equal to the margin of error. Okay, now if you look at the formula we had before, the number of people questioned would fit Z sub alpha over 2 divided by sigma squared, divided by X, the margin of error, squared times sigma squared. And that's the same thing as, in our case, Z sub alpha over 2. Let me bring the sigma, okay. Now, I can take this sigma and I can bring it inside, so instead of being sigma squared outside, it's sigma inside. And then we saw that the maximum value that sigma could be, in our case, is 1/2. Because the maximum value of the variance, sigma squared, was 1/4. So if I bring that inside, I can write that as 2x squared. Okay, so what I'm doing here is I'm taking sigma squared, I'm replacing it by 1/4, and then I'm taking the 1/4 and writing it as a 2 in the denominator inside the square. And so this gives me the relationship between the sample size, the margin of error, and the level of accuracy that I want in the confidence interval. Remember, the Z is defined by the confidence interval probability, the X is the margin of error, the N is the number of people I have to question. And it's related by this. So if I question at least this number of people, then my confidence interval will be at least a 1 minus alpha confidence interval. Okay, so let me put in some numbers here. Suppose that 1 minus alpha is equal to 95%. And suppose that the margin of error is 4%, because remember, it can be anything I want. So suppose I made it 4%, then I would find that N is equal to 1.96 divided by 2 times 0.04 squared. And if you work that out, that's about 600. So what this says is if I want a 95% confidence interval with a 4-point margin of error, then I will get that if I question 600 people. Suppose that I wanted a 99% confidence interval. Okay, now 99% confidence interval, of course, is better because that means that the likelihood that the true answer lies in the interval is 99%, not 95%. Because remember, if the true answer is 95% of being right, then it has probability 5% of being wrong. Okay, so here's 1 minus alpha is 99%, and now let me take the margin of error to be 3 percentage points. If I did that, then I would find that N is equal to, okay, now the value that fits here is not 1.96 because that's for 95%, but now I'd have to go to the table and use the value for 99%. If you did that and interpolated, you would find out that that value, instead of being 1.96, is 2.575. If I divide that by 2, times 0.04, 4 percentage points of error, and square it, then I will find that the answer is 1036.
0.03 squared.
What was that?
2 times 0.
You said 3%.
Let's see. Yeah, I copied wrong here. The way I have it is I want 4 percentage points. Okay, so here is a 95% confidence interval with 4 percentage points. Here's a 99% confidence interval with 4 percentage points. The difference is that in order to go from 95% confidence to 99% confidence, I have to go from 600 people to about 1,000 people. All right, suppose that, back over here, suppose that 1 minus alpha is equal to 95%. So now we're going back over here. But now I'm going to take the margin of error to be 3 percentage points, which is the one that we already looked at. And I would find, let's see, no, we look at 3.5 percentage points. So I'm just making these up. I would find from the formula that n is equal to 1.96, that's because of the 95% confidence interval, divided by 2 times 0.03, because I have 3 percentage points of error. Formula squares it, and that turns out to be 1067. So if you compare these two, you can see that 1,036 people and 1,067 people, that's roughly the same number of people. So for the same number of people, I could interpret the results as being within 4 percentage points with probability 99%, or being within 3 percentage points with probability 95%. In other words, if I make the interval narrower, which gives me more precision, then I lose accuracy. So if I allow a larger margin of error, I have a larger probability of being within those limits. So when you see the number of people that are questioned, you can't tell what's going on. I have to give you at least 2 of these 3 figures to figure out what's going on. And I can interpret it either way I want. One more here. Suppose that 1 minus alpha is equal to 99% again. And now we'll take the margin of error to be 3 percentage points instead of 4 percentage points. And in that case, it'll turn out that n is equal to, using this formula, it's 2.575 divided by 2 times 0.03 squared, and that turns out to be 1,842. So if I want 99% accuracy within plus or minus 3 percentage points, then I have to question about 1,800 people. Still, it's a relatively small number. So for example, if I'm doing this and I predict the results of the presidential election and I question 2,000 people and I predict that with probability 99% lie within 3 percentage points of whatever the poll shows me, then that indicates, people say that's not really right, that can't be because you only tested 2,000 people and we're talking about the election in which 100 million people are going to vote. So how can this 2,000 people reflect the results of an election of 100 million people? And the answer is, well, it doesn't matter how many people are voting. The bigger the better, in fact, because what this says is that if we had an infinite population, then if we sampled 1,842 people, the chance is 99% that the result would predict the correct outcome within 3 percentage points. So it's true, because it makes people angry, and they require people not to put these things on TV before the election is over. But if the sampling is done properly, then it's very accurate. Then the predictions are good. Now, I also from the newspaper, let's see. Okay, here's something from the presidential election. It says there was a poll, and there were actually several polls. It says the CNN Time poll was conducted Friday with 1,154 adults and had a margin of error of 3 percentage points. The Newsweek poll was conducted with 1,000 adults Thursday and Friday and had a margin of error of 4 percentage points. So they tell you, after they give you all this detail, they have 2 polls, CNN Time and Newsweek, and they tell you how many people they questioned, and they tell you what the margin of error is, but they don't tell you what that means. They don't tell you what the level of confidence is. But what it amounts to with our figures is we could go backwards and we could say, well, the margin of error was 4 percentage points, and there were 1,154 people. Well, that's not too far from 1036. Wait a minute now. No, that was Newsweek. Let me say this again. The 1036 was 4 percentage points, and Newsweek poll was 4 percentage points, and they questioned 1,000 people. So it's not unlikely that those 1,000 people with 4 percentage points margin of error corresponded to a confidence interval of 99%. On the other hand, CNN Time, over here, they questioned 1,154 people, and they had a 3% margin of error. And 1,154 isn't all that different from 1067, so it's likely then that this corresponded to roughly a 95% confidence interval. So this stuff is there in everyday life, except that it's really too complicated for to be written down in an ordinary newspaper. You'd have to have the New York Times or something like that, and it's certainly too complicated to be said on a soundbite on TV. But you could see that underlying a lot of assumptions that are made or interpretations that are made of what's going on in the world are based on these kind of statistics, which at heart is the central limit theorem. Let me give you a famous example of when things were screwed up, and I guess there's two things here. One is that one of the reasons that there was so much problem with the Bush-Gore election was that when they took the samples, the values always turned out to be very close to 50%. So the winner is the one, at least in a Democratic election, the winner is the one that gets the most votes. So we only have to have slightly more than 50%. So if the poll shows that the result is very close to 50% and you have a margin of error of a couple of points, then it really doesn't tell you very much and you're in trouble. All it can tell you is that the election could go either way. It's essentially what they call a statistical tie, and so that's what happened in that election. You couldn't predict it because in order to have a margin of error small enough so that you could tell a difference between 49.9% and 50.1%, you had to question everybody in the population. That is, you had to hold the election. And in that election, even the result didn't matter, because when it turned out that Gore won more than half, they still gave the election to Bush. But let's not get into that. Turn off the TV cameras. Okay, the other thing is that there's a famous election that happened in 1948. Most of you probably don't remember it. I don't remember it either. I just read it in the history books. But the 1948 presidential election had Dewey, who was the Republican, and Truman, who was the Democrat. And probably none of you remember Dewey because he lost. But 1948, that was just after World War II, and Roosevelt had died, and Truman was his vice president. And so Truman became the president, so he was the incumbent, so that gave him some advantage. But on the other hand, he was basically not very well known. He just became president in a sense by chance. And in any event, it was this election, and so a poll was used. This is one of the first times that these polls were used to predict the result of an election. And the polls showed that Dewey was going to win. And the people who conducted the poll were so sure about it that the Chicago Times had a big publication. Remember, this was the old days, so you couldn't publish things instantly. So the night before the election was held, based on the polls, they were so sure, they published a big headline that said, "Dewey wins," or something like that. Covered the whole newspaper. And of course, as you know, Truman won, because nobody remembers Dewey. So Truman won the election, and there's a famous picture of Truman after the election holding up the newspaper with the Dewey wins headline with a big smile on his face. But the question is, what happened? How could the statistics be wrong? And the answer was that the statistics were not properly taken. Nowadays, everybody is very sophisticated with respect to this stuff. And so the polling agencies, they don't just sample blindly, but they have to make sure that they sample properly. So if there are subpopulations, and they have to make sure that the subpopulations are properly represented. For example, if it turns out that some state is some state tends to be Democratic and another state tends to be Republican, then you would have to make sure that you weight things properly so you take that into account. So what happened in the Dewey-Truman thing was that the way they conducted the poll was that some reporters got on a telephone and they called people up and they said to them, well, who are you going to vote for, Dewey or Truman? Of course, there are always the problems that the people, when they're polled, might change their mind between the time they're polled and the time of the election. They might lie, who knows. But assuming that you don't have those kinds of problems, what they did is they called the people up and they said, who are you going to vote for? And of course, more people said they were going to vote for Dewey. So why did they get the wrong, why was their sample biased? Well, one reason was that they got the sample by using a telephone. And in 1948, not everybody had a telephone. So it tended to be that the people who had telephones were the wealthier people, and the people who did not have telephones were the poorer people. And so by calling people whose names were in the phone book who had telephones, they were biasing their sample towards wealthy people who tend to be Republicans, so they got an overrepresentation of Republicans in the sample compared to the actual vote. Also, being the old days, these guys worked 9 to 5, and so they called up people in the phone book, and of course they got people at home. So who is at home? I mean, the Democrats are out working, Republicans are home eating bonbons and watching Jerry Springer or whatever they do. And so the end result was that they overestimated in their sample the number of Republican voters, and that's why it didn't work. But they've learned a lot since then. Now if you look at these statistics, they're almost always right. So the bottom line is that this stuff is actually very important in everyday life, not only in terms of engineering and queuing and stuff like that, but also in terms of things like election polling and public opinion polling. Okay, are there any questions or comments about this? All right, so now you can go on forever. For example, I'm not going to go on forever, but what we did is we took the maximum value of sigma. But maybe you don't want to do that. So there's another way you could get sigma, which is you could estimate it from the sample. Because remember, we did that with our simulation in homework 3, which is we took the sample and we took the sum of the squares of the x's, we subtracted the square of the average of the x's, and the result was that we got an estimate of the variance, and it turned out that that was very accurate. But it's not 100%. And so if I use the same sample to calculate the average and the variance, then I've got some kind of problem in that I'm using the same data twice. So what do you do about that? Well, the answer is that there's an additional theory, which is much more complicated mathematically, which takes that into account. And in fact, you can now go on and you can ask questions about changing all kinds of assumptions and making things more and more complicated. And theoretical statistics is concerned with being able to understand that, derive formulas, and practical statistics is concerned with doing the best you can to use these formulas in real-life applications. So this stuff here is just the beginning, but in the end, it's all based on the central limit theorem. Okay, so are there any questions about the exam, the course, who's going to win the next election, any of those things?
The exam is based on the central limit theorem and
the exam is going to be based on the homeworks. Homework number 5 concerned the central limit theorem. But you didn't have to hand it in, but you're still responsible for it. But this kind of thing is more sophisticated than I would do on the exam. But remember that in the central limit theorem, although I've been doing it making statements in terms of average values, an average is just a sum divided by a constant. So there are different ways that you can present the statement about the central limit theorem, different ways of writing it. Just like here when I wrote the statement about the confidence interval, what I did was I changed things so that they were algebraically equivalent but looked different. So I've been emphasizing X bar, but doesn't have to. I just wanted to make that point. But otherwise, the exam will be based on homeworks, and there'll be nothing specific from the midterm, although the basic ideas of probability, which were used in the midterm, and were also used since the midterm, they'll still be there somehow. Okay, anything else? Okay, well, good luck.